Hi there. Today we'll look at object-centric learning with slot attention by Francesco Locatello, Thomas Kipf, and others of Google Brain, ETH Zurich, and MPI. On a high level, this paper recognizes scenes of objects from single pixels, and it's best I show you a picture of what's going on. So you have scenes like this, where there is some sort of an arrangement of objects, and there are multiple tasks you can do here. Specifically, they consider the task of unsupervised recognition of objects, which they call object discovery, and supervised classification of objects. The difficulty being that these are sets of objects, so there is no ordering to the sets. They do this via a thing they call slot attention that basically is a permutation-invariant attention mechanism over these objects in both the supervised and unsupervised domain. And they do this in a fashion where they iteratively route the attention in order to make the different slots compete for attention over these objects. So that's the sort of high level. If you are in this field, you probably know right now what's going on. If you're not, we'll dive into it together. So stay tuned. If you like content like this, consider sharing it out, leaving a like, or tell me what you think about it in the comment. I appreciate any suggestion for making these videos better and so people can learn more from it. All right. So the problem, I've already described the problem a little bit, but let's go a bit deeper here. You have images like this, and the images we're considering are going to be images that have some sort of arrangement of objects, or what we humans would call objects. In this case, you can see there is this gray square, this gray cube right here. There is a smaller green cube, and then there is a yellow cylinder. Now, in the task of object discovery, what you're supposed to do is you're simply supposed to say that there is an object right here, there is an object about here, and there is an object here, right? So basically you're supposed to point to the pixels where there are objects, and you're supposed to segment the objects from each other. You can see right here that this model, we don't know how it works yet, but it separates the left cube here, the bottom cube here, and the top right cylinder right here. In the task of set prediction, you're supposed to say what objects there are. So you're supposed to say there is a gray cube right here, a green cube right here, and there is a yellow cylinder right there. Actually, you don't have to say where they are, I guess. There are many different variants of this task, but mainly you're supposed to classify them, meaning you have to say there is a gray cube there. I believe in this case it's with coordinates, but you can do it without. The difficulty here, of course, being that these are sets, so there is no natural order in it. So if you say there is a green cube and a yellow cylinder, it's going to be the same as there is a yellow cylinder and a green cube. So you'll have to build an architecture that is somehow invariant with respect to the labels. And we've seen a lot of the concepts in this video, in this paper before. This video is sort of a kind of a mash together of different concepts of other places. So what you'll see is, for example, this property of the fact that here you see are the labels for these objects. This could be there is a green cube, there is a gray cube. And you'll have to come up with an architecture that if here you predict that green cube, you consider it correct, even though the corresponding label isn't the one for the green cube. And we saw this, for example, in this DETR architecture by Facebook, where they use a matching loss, but we'll get into that. Okay, so these are the tasks. The tasks are object discovery and set prediction. So how does this paper deal with this? They use this thing called a slot attention module. Now, the slot attention module is, in essence, it's pretty simple. What it does is it has these different slots right here, as you can see. And it divides the input into features. So you can see there is a CNN encoder because we're working with pixels. It's natural that we want to encode these into a CNN. This CNN will probably downsample the image a bit and subdivide it into this grid right here. So you have a fairly coarse grid. The grid is actually not a bit finer than you see here. This is just for example. But you'll have ultimately a number of features. So each pixel right here is going to be a feature. Each feature will have not only this one channel as you see here, but many, many channels of information down here. So the CNN will encode each of these regions in the picture into a feature vector. And then you have these slots. So what you'll want to do, we maybe look at this. So you'll have the features right here. These are your features. And you'll have the slots. And the slots, let's say there are fewer slots than features. 2, 3. 3 slots. 4 slots, as in this case. 4 slots. What you'll want to do is you'll want to assign the features to the slots. So you maybe say, okay, this feature right here and this feature right here, they go to this slot. And then these 2 features go to this slot. And these 2 go to this, and that feature goes to that. And that's equivalent to basically subdividing the picture into these slots. Ultimately, your goal is going to be to say that these features right here, these pixels right here, are going maybe into that slot, and then these ones right here are going into that slot, and these ones here going into that slot, and the rest, so all of the background, is going into that one. You can see that if you have a system like this, if you can train it correctly, then it becomes pretty easy to, so it becomes super easy to classify it right here, because you can just take each slot and independently classify it, right? Because you already know, you already have assigned all the pixels where the object appears into that slot. You can just super easily predict a class from it. So we're almost at the end. So you now predict for each slot a class or a description of the object, whatever you want to predict. And this is the exact same thing as in this Facebook paper now, where for each of these slots, we've predicted a bounding box. The question is, how do you assign this to the labels? And that's pretty easy. That there's this thing called the Hungarian matching that basically what you're saying is you want to be as forthcoming as possible, right? So if you predict a gray cube somewhere and there is a gray cube somewhere here, you want to match them. You'll say, okay, I'm going to give you the benefit of the doubt, and I'm going to, dear model, I'm going to assume with the gray cube you meant that gray cube right here. And if there is the yellow rectangle and the yellow rectangle somewhere over there, you don't incur any penalty as long as you predict the correct things. Now, only whenever you predict like a second yellow rectangle. So both of these slots, now, so this slot and this slot, for some reason, they predict a yellow rectangle. This one correctly, and this one was assigned this object, and it incorrectly predicts a yellow rectangle. Oh, sorry, other way around. This one incorrectly predicts a yellow rectangle, where there's no second yellow rectangle in our label set. There's only this, maybe this green cube. Then this will be a mistake because it can't be matched. It will be matched to the one where it has the least loss, but it will be matched to something that's not a yellow rectangle, and therefore that's going to be a mistake. So this is how you calculate the loss function with this matching algorithm. And you can calculate that matching in a deterministic fashion, so you can backpropagate through it. So you can see if this slot assignment works, we'll have a pretty easy time then calculating the classes, coming up with a loss. The same for the unsupervised object discovery. What we'll do is we'll run these things through this slot decoder. Now, this slot decoder is very similar to a generator in GANs, for example. It takes a hidden representation as input. Now, the hidden representation here is going to be these slots, and it's going to upsample it into an image. if we train the whole, if we have a good slot assignment mechanism, we can pretty easily train a decoder like this, right, with any method you want. In this case, I believe they use some sort of upsampling, up-convolution architecture right here, and they use the L2, they minimize the reconstruction error between the output image and the input image. So it's sort of like a variational autoencoder or just autoencoder objective in this case. All right, so we know how to encode a picture into a hidden representation using a standard convolutional neural network. And we know once our slot attention mechanism works, we pretty much know how to go from there. So the question is, what is this slot attention mechanism? Now, what we're supposed to do is we're supposed to, again, assign each one of the features into a slot, and in a very specific fashion. So if you think about the pixels right here, there can be multiple of these pixels or multiple of the regions, multiple features can be assigned to one slot, but we'd rather not have the same feature assigned to multiple slots. So each slot takes in many features, but the features should be divided between the slots such that only one slot attends to a feature. And by me saying attend, you probably already know where this is going. So if you have the features and you consider the slots, right? And we just look at a single feature for now. What we'll do is we'll have an attention mechanism from the slots going into the features. So if you don't know what an attention mechanism is, I have this video called Attention is All You Need, where I explain this. But briefly, the features, they will emit something that's called a key, which is a vector, and then the slots will emit a query, which are also vectors. And the information is now routed by agreement of key and query. In this case, this feature right here would be routed to this slot. Now it would be routed to both slots, but it wouldn't be routed as much to the bottom slot. And we make sure that this happens by using a softmax assignment. So if this is like 9 and this is 4, what we'll do is a softmax assignment such that after that, so we have a proper distribution, which would be something like, after the softmax be something like 0.9 and 0.1 right here. So you can see that the attention is fairly hard. So this is basically, it's a differentiable way to assign these things. Okay, so an attention mechanism fulfills the property that we want to basically assign features to the slots in a way that the slots compete for the features. As you can see right here, if this slot here matches the feature the best, it outcompetes the other slot, because at the end this has to be normalized to 1 because of the softmax. So this competition is the heart of the slot attention mechanism. And this is how it works. So this is the slot attention module, as you can see. So you'll take your inputs, and they have lots of layer norms in here, but disregard the layer norms. So what you'll do is you'll calculate the agreement between the inputs and the slots. Now you might wonder, in a standard attention mechanism, you'll have input signal coming from here, which is like, maybe these are the input signals, and then you construct the keys and the queries for the next layer. You construct all from that input signal, right? And also the values, by the way. You construct everything from that input signal. But in this case, we'll have many features and we'll only have a fixed amount of slots right here. So where do these slots come from? Where do the signal for the keys come from? In the Facebook DETR paper, we saw that these are learned embeddings. However, in this case right here, these are not learned. The slots are initialized randomly. So at the beginning of each thing, the slots are initialized randomly. You can think of this as an attention mechanism where you have the attention module right here. And then at the beginning, you simply have randomly initialized positional embedding or randomly initialized slots. And then the image is going to be encoded through a CNN right here, giving you a bunch of these features. And then you'll have cross attention between these features and the slots. And that will give you the next layer right here. Okay? All right, so you want to calculate the routing between the inputs and the slots. And then you want to perform a softmax over the slots, which will give you this competitive nature between the slots. So all the slots are going to compete for the features to be routed to them. And then this is simply the second part of the attention mechanism. So you'll have a weighted mean. Now this is a slightly different from an attention mechanism, because in a real attention mechanism you'll have a weighted sum right here. Here you'll have a weighted mean, but it's basically such that you can have a different amount of slots and the kind of values will stay the same. That's why you do the mean. So you weight them up and the values are simply a function of the inputs. This is like in a standard attention mechanism. Then what you'll do, you can see that this is now called updates. Okay, so you start with the slots randomly, and then you use the slots to route the information. You take the inputs and you use that information routing to calculate the updates. Now you put the updates through a GRU with the state being the previous slots, and then you'll add that to the slots. This says optional residual MLP. So what you can do is you will have a residual MLP or not. This is a fairly complicated thing, but if you think of it, it is just a transformer. So what they describe here, the purpose of this GRU here, of course, is that the GRU is a recurrent unit. And you can see right here that they do this multiple times. So once you start with the random slots, right? But then you update the slots and you go again. Okay, so you do this. First of all, you'll have the features and you'll just have random slots. And then you do a bit of routing. Okay, so now we have a bit of routing. Cool. You update these slots to be the next set of slots. And then you take the same features and route them again. So you route them again. And this is supposed to be kind of this iterative procedure. You might have seen this in capsule networks. I've done a video on capsule networks where exactly this type of iterative routing, you always have the same routing functions, right? These the functions for value and key and query are always the same, but you do this iteratively many times in a row. This is like a transformer with weight sharing. It's exactly the same, right? So you have these slots, you initialize them randomly, you do your query times keys, your softmax times the value right here. And the transformer even has this plus this MLP layer right here, right? The transformer has that in there. And then you simply do it again. So up here, you have the next transformer layer, but instead of being its own layer, you'll copy, so it's weight shared. It's a transformer with weight sharing between the modules, and the inputs, they are also copied up here, these side inputs. All right? Otherwise, it's the same thing, except that these aren't produced by an encoder that is also a transformer. They're actually produced by a CNN, and the weights here are shared. The only difference is that in between here, they also have like this GRU thing. But they do an ablation on it, and it's actually not that important. So you might as well just leave it away. It brings only very few benefits. So this is how I think of this model. This is a multi-layer, a T-layer transformer with weight sharing for the individual layers, where the inputs, the input positional encoding, are randomly initialized each time. Okay, now they really stress this random initialization because this differs from the DETR paper in that in the DETR paper, these things here are learned. In the DETR paper, we have also this kind of object detection thing. And what will happen when you learn these is that, for example, this one right here might specialize in objects that are sort of on the top left of the image. And this one might specialize in objects that are kind of long and in the middle and so on. And this one might specialize to something else. Now, I can't tell you what works better or what not. It seems like you can, if I were to implement something like this, I might want to go with the Facebook one and then just have more right here. In this paper, they opt for having fewer, but because they're fewer, if you learn them, they become, I guess, too specialized, and you will need to keep them agnostic. So you don't want to learn them. You simply want to randomly initialize them each time. And via the iterative routing, via the weight sharing, they will be sort of assigned correctly. All right. I hope you could follow this. Yeah. If you want to anthropomorphize this, you could think if each of these slots starts out just randomly. And then just by sheer coincidence, through this attention mechanism, they happen to be assigned a couple of these features. Now, because we train the model to perform well, because they're already assigned these features, in the next layer, they'll basically ask through the query function, they'll ask for more of that. They'll basically say, oh, I'm now responsible kind of for the gray pixels. Give me more of the gray pixels, right? Give me more of that. And then in the next layer, even more of that, even more of that. And you'll see in the investigations into what happens exactly this type of thing happening. So if we skip ahead to the experiments where they show what happens through the iterations, you can see this right here. So the attention maps of these slots, you can see that after the first step, you can see that, it's slot 2 right here is assigned kind of both of these objects. Slot 3 is already pretty, so the first step kind of learns to segment a little bit of the image, but not too well. Slot 4, also the attention map here is pretty wonky. But if you, in the next step, and this is kind of crucial, basically these slots, they specialize. So slot 2 realizes, well, I have a lot of these blue pixels, so I'm gonna give me more of those, right? Give me more of those. So it gets all the blue pixels. Well, slot 4 has a lot of these golden pixels and says, give me more of those golden stuff that's also regionally right next to that. And since these two compete, I'm pretty sure slot 2 would also ask for more of the golden pixels because it has a lot of golden pixels. But it competes with slot 4 because of the softmax. So all of the golden pixels are assigned to slot 4 and not slot 2, while all of the blue pixels that slot 4 surely asks for as well are assigned to slot 2 in the next iteration. So I actually consider iteration 1 is for you take the randomly initialized slots and you kind of assign them stuff. So this is now mainly the transformer layer learning to segment. But then step 2 is where the magic really happens, is where the slots, they kind of realize what's assigned to them and they ask for more of it. And through the competition, you'll get this separation into objects, right? So the whole thing is trained end to end, which basically means that these functions get really good at doing this kind of segmentation. All right, and then in subsequent iterations, you can just see this effect multiplying even more and more, right? But you might even be able to think that you might want to separate step 1 and the subsequent steps, because step 1 seems fundamentally different from steps 2, 3, 4, and so on. Because step 1 is this kind of assignment process, and then the other steps are refinement. So if I were to take this model and make it better, I would try to have a special, like, not weight sharing between steps, the first step and the subsequent steps. But what do I know? These apparently it works okay. You can also look at the reconstruction, since their objective is to reconstruct. So basically what each slot outputs, if you reconstruct each slot here, these are the different slots. Each slot is supposed to output a picture of the reconstruction. Now, if we consider that each slot is responsible for an object, you might very well say, okay, this slot here gives me a picture with just the object in it that it's supposed to reconstruct. And then this slot here gives me a picture with just the object that it is supposed to reconstruct. Now, how do you know how to combine these pictures, especially since they might be overlapping and so on? So the way you do it is you actually output 4 channels. So you output R, G, B, and A. So A being the alpha channel. So each slot also has to decide where the object is that it reconstructs. And so this here might be, okay, everything here is alpha 1, and including the shadow, maybe there's a little shadow, and everything else is alpha 0. And then the alpha maps you combine also via a softmax to ensure that they sum up to 1. So you combine the pictures including their alpha maps. But that means you can basically reconstruct from the slots where the objects are. Now you'll notice, this is this thing here, you'll notice that they often use, for example here, 4 different slots, because even though the image has 3 different objects. Why is that? Because you need to reconstruct the entire image. So you need at least 1 slot for the background. And that's always what you can see right here. So if you have the reconstruction, you'll see that slot 2, with iterations, it reconstructs this cube. Slot 3 reconstructs the little ball. Slot 4 reconstructs the yellow cylinder. And slot 1 reconstructs the background. Okay. Also here, if you see the attention masks, you see that the slot 1 will be responsible for the background. Here the background is significantly darker than in these others. Though they do say the background doesn't really tend to go to 1 slot in particular. It tends to kind of spread out across all the slots. And this might mean more investigation. Yeah. So they have these different tasks right here. For example, to segment these Tetris blocks here. And you can see the segmentations. It works pretty well. Now, why does this work so well? It's probably because of the data sets. So these kinds of data sets, they come, they're produced by a generator, and the generator specifically has these objects right here, and it sort of it arranges them in an independent fashion. The background is really clean, right? The objects themselves are really clean and geometric and so on, and they're kind of arranged in a random fashion, and then there's a render of that. So this is like super duper clean data set, and I guess that has a lot to do with why these methods work so well, because they can just assume, okay, an object is generally, spatially some geometric shape that I know, it's close together, it's pretty independent from its surrounding, and it's trained with objects that are almost 0 correlated. Like there's 0 correlation between the objects in the training data set. So I wouldn't yet apply this much to real world problems, but it is an interesting thought right here. So that's the sort of idea behind the paper. I hope you got that. They do a lot of experiments, and here is a bit where my quarrels start. So they say that they compare, for example, with these in the unsupervised object discovery experiments. They have this data set called Clever. And this data set has these images with sort of, I believe Clever 6 has up to 6 different objects. Now this is already one of the things. This is not a specifically quarrel with this model, but if your data set has 6 things, they give 7 slots because they know that the data set has at most 6 things, which means they can always cover all the things. Now it works when there's less objects, but I think the knowledge of how many objects there's going to be is also a big part of why these models work and why maybe it's not entirely ready yet for the real world. But anyway, they compare to these 2 baselines. They're called iodine, which also employs kind of a recurrent architecture, but not with an attention mechanism, and Monet. And they say, yada, yada, yada. This replaces slot. No, that's not it. For the Monet, iodine, DSP, and baselines, we compare with the published numbers as we use the same experimental setup. So they say they use the same experimental setup, and that's why they don't re-implement these models, but they use the published numbers in their respective papers, which is something you can do. This is often, I guess, these machine translation papers and so on, they do this just because, you know, it's a lot to run these things. However, here I'm a bit skeptical. First, yes, because it is Google, so they do have a lot of resources available to technically run these things. I've seen at least Monet has an implementation by the author, or I've seen one of them. The other one also, there is an implementation, and there's 8 authors on this particular paper. So this would be okay, they say, as we use the same experimental setup. So in that case, if you have the same setup, it's more okay. But it really depends on you really having the same setup. And this is a bit where it kind of falls. So for example, one example right here is they say we train using the Atom optimizer with a learning rate and 60 so on. They use a single GPU. We further make use of learning rate warm-up to prevent early saturation of the attention mechanism and an exponential decay schedule in the learning rate, which we found to reduce variance. So I've checked these other models and none of them talks about learning rate warm-up, and nowhere in their code is there a learning rate warm-up. Now, you might argue, okay, this is specific to this model, it might need this, but if you look at the results right here, for example, you see that they don't outperform these other models by too much. So you can see right here, this is on par. This here outperforms this one a little bit, but then also the star here means that they have left out one of the denotes that one outlier was excluded from evaluation. I guess it is valid if it's a super outlier, but in this case, I would categorize this model as a different way of doing things and not necessarily outperforming the others. So this also, if you look at the ablations, the differences here are minuscule, and in these ablations that they show, every single thing they do like gives them a little bit of a boost, and you just make it kind of across the line to reach state of the art. I'd rather have research move in a direction where we just show cool ideas and that they work, and that's what this paper does to be fair. What I do have more of a problem with a little bit is this here. On Clever 6, we can use a batch size of up to 64 on a single V100 GPU, as opposed to 4 in this iodine baseline, right? Compared to iodine, our model is significantly more efficient in terms of both memory consumption and runtime, which is, something I believe, but this characterization that they use a batch size of 4, and here in this paper, they can use a size up to 64 on a single V100 GPU. I've read the iodine paper, and the iodine paper says, yes, they do use a batch size of 4 on one GPU, so they also use one GPU, but they say their GPU has a RAM of 12 gigabytes. And 12 gigabyte RAM GPUs, that points to something like a TI, either I guess a 1080 or a 2080 or something like this. This is not a V100. The V100 come in 16, or probably Google has the 32 gigabyte version. So this is a 32 gigabyte GPU that is significantly better than the TI GPUs. These V100, they cost like 5 or 10 times more than the TI GPUs. And to simply say, we have also one GPU and we can run up to a batch size of 64 and they can only run a batch size of 4, it seems, I don't know, it seems sort of overstating what you can do. Now, maybe I'm wrong. Maybe they have actually tested this other model and concluded also on their GPUs, it can only run to a batch size of as a batch size of 4, but I highly doubt it, because here the paper is cited, and in their paper they explicitly name that they use a batch size of 4 for their 12 gigabyte GPUs. So yeah, that just kind of pulls through. So there's the minuscule improvements, and then there's the ablations of all these tricks where everyone just gives you a little bit, and then there is this kind of very, very, very favorable comparison wordsmithy a bit, which gives a bit of a bitter taste to what I think is actually a very, very cool method. Because why is this method so cool? Because, for example, these slots here, they are trained to also absorb the background, right? So you can technically, at inference time, increase the number of slots, even though you've trained with a few slots, right? You can increase the number of slots, and the model can just handle it, and they show it right here in these results. Here, this data set has 6 objects, and this data set has 10 objects. Now, the model has only been trained ever on 6 objects, and they can just up the number of slots at inference time, and it'll work also very well. Also, they can now up the number of iterations. Since these are all weight shared, these iterations, right? We've looked at it. There's weight sharing between the iterations. There is nothing stopping you from just piling on here. Because it's weight shared, you don't need any more weights. You can just refine this iteration. And since the iteration themselves are refining these attention masks anyway, you might as well, at inference time, refine them some more. They have an ablation where they show that technically like 2 or 3 iterations at training time gives them the best result. I guess just because of gradient propagation, because more layers means you have to propagate the gradient back more. But at inference time, you can just up these iterations, and as you can see right here, you get better and better. So these results are pretty cool. They respect the property that sets should be permutation-invariant and so on. This routing view of the transformer is pretty cool, even though it's you can look at it as a transformer with weight sharing or an iterative routing protocol like in capsules. So all of this I find to be a very, very cool idea. And I think that's how we should look at this paper. So before I am too critical of this paper, I want to say that I really like the idea and the algorithm here, the implementation. Yeah. So that was the paper. At last, I actually want to look at the broader impact statement, just because I've complained about the need for broader impact statements. So I just want to kind of just read them and look how the different companies, how the different institutions, how the different people, how the community reacts to them, crafts them, and so on. So this one I find particularly interesting. Let's go through it. It says, the slot attention module allows to learn object-centric representation from perceptual input. Okay. As such, it is a general module that can be used in a wide range of domains and applications. In our paper, we only consider artificially generated dataset under well-controlled settings where slots are expected to specialize to objects. However, the specializations of our model is implicit and fully driven by the downstream task. We remark that as a concrete measure to assess whether the module is specialized in unwanted ways. One can visualize the attention masks to understand how the input features are distributed across the slots, while more work is required to properly address the usefulness of the attention coefficients in explaining the overall predictions of the network, especially if the input features are not human interpretable. We argue that they may serve as a step towards more transparent and interpretable predictions. This is it's a fine statement, but it's not a broader impact statement, right? If you followed a bit what the broader impact statement is supposed to be, this is not one. Okay, the closest this comes to a broader impact statement is said, as such, it is a general model that can be used in a wide range of domains and applications. And maybe a little bit that you can visualize the attention masks to understand how the input features are distributed. But the broader impact statement is supposed to give you a preview of how this might affect society at large, while this here just kind of lists properties of the model for the research community and sort of for this for the application of this model as you know, the introspection of the model itself. This says nothing about society as such. So maybe that's, I think that the smarter people will turn the broader impact statement into more of an introduction section, because that's something you usually put in a conclusion or in an introduction, where you say, look, here are some things our model can do, and this is what it might be useful for, and this is how you could introspect it, and so on. And since the broader impact statement, especially at NeurIPS, you were allowed to put the broader impact statement on the main paper, so not in the appendix, but it wouldn't count towards your page limit. It's, I guess, pretty foreseeable that what people are going to start to do is simply put more of their paper into the broader impact section, kind of cloaked in the veneer of a broader impact statement. But this is clearly not what the broader impact statement was originally supposed to be. Now, I don't know if this is good or bad. I just think these authors are, they're doing, I think, a good thing here by simply telling us actually something useful about the model. But that's just my opinion. I do thank you for being with me here. I know this was a bit ranty, flip-flopping back and forth between the different things. We haven't looked at set prediction at all. We've only looked at these kind of masks, but I invite you to go through the paper yourself and check it out. It's pretty cool, and they do describe a lot of things in pretty detail. The appendix is very long and has very many ablations, and this is something I do appreciate. And with that, bye-bye, and see you next time.